All right, everybody. So the next question we're really interested in for power series is, well, what is the domain of a said power series? So remember, we're thinking of power series as functions. And for functions, we like to know, well, if I give you an x value, you're going to give me back some output in return. And for functions or power series, we're thinking about that same question. What x values are we allowed to evaluate that power series at? In other words, if I put an x value into a power series, am I going to get a convergent series? If that series converges for a particular x value, then we say that x value is in the domain of that power series. In other words, we can evaluate that function at that x value and get something meaningful in return. So let's go through the following example. We have some function that we're defining as a power series, the power series from n equals 1 to infinity of n over 5 to the n power, all times x to that power of n. So remember, what we're wondering is, if I do something like f of 0.7, am I going to get a value back from that series? Is that series going to hand me back something convergent? Or is it going to give me garbage because that series actually diverges at x equals 0.7? So that's really what we're wondering here. And well, before we get into it, I mentioned earlier, very briefly, ratio test is really going to help us out here. And that's really the first step of what we're going to do. So let's actually apply ratio test to this power series. So remember what ratio test was. We take the limit as n goes to infinity of the next term of the series, the n plus first term. So what that looks like in this case is anywhere we have an n, we're again writing this as an n plus 1. So we have n plus 1 all over 5 to the n plus first, all times x to the n plus first power. And we divide that by the nth term, which is n over 5 to the n times x to the nth power. And that's all wrapped up in absolute values. So remember, for ratio test, what we want is this to be less than 1. When this limit is less than 1, our thing is absolutely convergent. So let's see what happens in this case. So we take the limit as n goes to infinity. We still have those absolute values. The first thing I like to do in these problems is just rearrange the terms so I don't make a silly algebraic mistake. So for example, I'm going to kind of put like terms on top of other like terms. So this actually becomes an n plus first all over n times 5 to the n all over 5 to the n plus first times x to the n plus 1 all over x to the n. And remember, when we divide by something in the denominator, especially if there's a fraction, we reciprocate that fraction and then multiply it onto that numerator, which is how I got to this second step here. So the reason why we do that is because at this junction, we can actually start doing a little bit of algebra. So for example, if we have 5 to the n all over 5 to the n plus first, we can actually cancel out a factor of 5 to the n. So we're just left with a factor of 5 to the first in that denominator. In a similar way, we can cancel out a factor of x to the power of n from both of those terms, x to the n plus first and x to the n in the denominator, and we'll just be left with an x to the first power in that numerator. So let me just clean up what we have so far coming from ratio test. We have the limit as n goes to infinity of the absolute values. We have n plus 1 all over n. And I'll just say, be careful with parentheses in these problems. It's really easy to lose parentheses. Times x to the first all over 5 to the first as well. And remember, what we want is this limit to be less than 1. All right, and I just want to emphasize this limit is with respect to n as n goes to infinity. So the only thing this limit really cares about are those n terms. This other term with x to the x over 5, we could actually factor out of that limit entirely since there are no n's on it. So actually, let's just go ahead and do that. We can factor that x over 5 out, and we have to maintain the absolute values. And then this is multiplying the limit as n goes to infinity of the absolute values of n plus 1 all over n. And well, we can do this limit. We see that as n goes to infinity, both the numerator and denominator are going to infinity, so we get to do L'Hopital's. The x over 5 in absolute values still hangs out in front, and we just did L'Hopital's on this limit, where the derivative of the numerator is a 1, and derivative of that denominator is also a 1. So I'll just be quick to say we did some L'Hopital's here. So this whole limit is just equal to 1. So coming from ratio test, what we're left with is the absolute value of x over 5. And this is a weird thing compared to what we've seen before for ratio test. When after we've completed the ratio test, taken that limit, we were just given a yes or no. Is this absolutely convergent? Is this divergent? Is this inconclusive because the limit's 1? Well, in this case, what's special about these power series, we get to choose the x values. And we can choose x values so that this ratio test limit is what we want and is less than 1. So we are basically saying we want this ratio test limit to be less than 1. And we get to choose x values to make that happen. And as a spoiler, this is exactly where the brunt of our domain of that power series is coming from. So at this junction, we have absolute values of x over 5 is less than 1. And well, we have this inequality now, and we need to solve for different values of x that make this work. So before we do anything more, we know that solving inequalities, we consider basically two cases. We consider the case where, well, the forward case, which is x minus or x over 5, excuse me, is less than 1. And then we also need to consider the other case where x over 5 is greater than minus 1. So let's see what happens in this case. Well, if we're solving, say, the left-hand side first, we're just trying to see what x values work. So it looks like when x is less than 5, we're getting some information about the domain. Now, if we look at the other side, when x is over 5 is greater than minus 1, well, if we solve for x, or solve for x in this inequality, I should say, we find that x has to be greater than minus 5 for the series to converge. So if we take both of these pieces of information, we can patch together a big chunk of the domain in which our power series converges. So if we take this minus 5, we know that when x is greater than minus 5, it looks like our power series is okay, but then we're also restricted by when x is less than 5 itself. So far, our domain is looking like x values are allowed between minus 5 and 5. But there's one thing we haven't done yet. We don't know what happens at x equals minus 5 or at x equals 5 for that matter. So let's just summarize where we are right now. So far, x values in this interval are allowed in our power series. Again, what this really means is if we use these x values in our power series, we get a convergent series in return. The one thing we don't know yet is what happens at the endpoints. What this really means is at x equals -5 and x equals 5. So we actually need to check these endpoints individually because again, where this inequality came from a few minutes ago was because when the ratio test gives us a value less than 1, we know it converges. But when the ratio test equals 1, it's inconclusive. So that's why we have to test next these endpoints individually. So that brings us to step 2. Step 2, test the endpoints individually. And what I really mean is we're literally going to put in x equals 5 and x equals -5 and assess whether that resulting series converges or diverges. So let's just remind ourselves what the original power series was. It was this function or this series from n equals 1 to infinity of n over 5 to the n x to the n. So just reminding ourselves what we're testing now. So we're basically asking ourselves, is x equals -5 and x equals 5 a valid value of x to plug into this function? So let's plug in x equals 5 first. So we're literally just asking ourselves, is f of 5 allowed? So when we do that, we're going to take our series that's on that right-hand side, and we're just going to plug anywhere there's an x, we're going to plug in the value of 5 and see what happens. So again, we're taking the right-hand side of our power series or our power series itself, and we're just plugging in a specific value of x and seeing if this resulting series converges or diverges. All right, so let's do a little bit of algebra here. So in this series, we have a 5 to the n in the denominator, and we also have multiplying 5 to the n in the numerator. So those two 5 to the n's cancel out. So we just have the series of n, which again, this series is, from n equals 1 to infinity, 1 plus 2 plus 3 plus 4 plus 5, etc. So hopefully by now we can get an intuitive sense, this series is not going to converge. But why doesn't it converge? We can try something like the test for divergence, where if we just take that series function, which in this case is, well, it's just n, that limit is equal to infinity as n goes to infinity, which is not equal to 0, so it diverges. So what we've just learned is x equals 5 is not allowed. Okay, so one of those endpoints, we know we can't actually evaluate that power series at 5. Let's check the other value. So what happens at the other endpoint, x equals -5? And again, what we're really asking is, if we plug in -5 into that power series, is -5 allowed? In other words, when we plug in -5, are we getting a convergent series that could give us something actually meaningful in return? So plugging in that -5. So we have into our power series. So anywhere there is an x before, we're just replacing that with a -5. So again, that means that last x to the n, we're just plugging in a -5 to the n. We can do a little bit of algebra here to cancel some stuff out. We have n over 5 to the n. We can break that -5 to the power n into two different factors. We can divide this, or sorry, break this up into a -1 to the n, and another term that is just that 5 to the n. Remember, if these bases are different, like in this case, we have the -1 and the 5, but we're raising them to the same power, in this case, that n, we could just multiply those bases together and then raise that product to the power of n. So that's sort of what we're doing, but in reverse here. And the reason why we just did that is, well, these 5 to the n's cancel out. So what we actually have here is, well, we have this series now of -1 to the n all times n, which is an alternating series. But if we just wrote out the first couple terms of this, we have -1 plus 2, -3 plus 4, -5 plus 6, etc. Our gut feeling is this probably is not going to converge. And in fact, we could hit this with the test for divergence and see that this limit actually does not exist. So if we take the limit as n goes to infinity of -1 to the n times n, this limit does not exist. So by the test for divergence, this series is divergent. Right, so what does that mean? Again, we're testing if x equals -5 is a point we're allowed to put into our series. And in this case, it is not allowed. So -5 is not in the domain. So if we go back to what we had before we tested the endpoints, we had this domain from -5 to +5, not including the endpoints. We tested the endpoints individually. It turned out that neither of those endpoints are allowed in our domain of integration. That's not always going to be the case. This is just a case in which that was a coincidence. Neither endpoint worked. That's not always going to be the case, though. So the last step is, of course, to put all this together. But nothing really changes. The domain of x that we're allowed just turns into what we had before. All x values between 5 and -5, not including the endpoints. So if we put any of those x values in there into our power series, it'll converge. And that's how we can figure out the domain of a power series. Step 1, hit it with ratio test. Step 2, test the endpoints individually. Step 3, put in what the endpoints do if it converges at an endpoint. If it doesn't converge at the endpoint, just leave them off like this case. And the last thing I want to say is, once we have that domain down, this is what we call the interval of convergence. Because again, if we choose any x value inside of that interval of convergence and evaluate our power series at that x value, we know it'll converge. So speaking like a function, we can give it an x value and that power series is giving us something meaningful in return because it converges.